All right, and so now the fundamental idea as well as the detailed explanations, all of the detailed explanations have officially ended at part 2 of our lecture, our general lecture on the substitution method. So the general lecture on the substitution method there was intended, and both parts there that both parts with the video that you have seen, those are intended for those were intended for general calculus students. Meaning, the ones with the material you've learned there, you can go into different career paths such as business field, economic field, or social and sciences, or even formal math major have to start out from that general understanding, or the engineering major and physics major. So that's what I meant by the general the calculus students. And so the two parts that you have seen previously were intended for general calculus students at any level. But now allow me to add to that general lecture a part 3. Now it's where I have examples and I bring up problems that are suitable and intended for students who are on track to a technical field, a technical career, such as a math major or engineering major, any kind of engineering major, or computer science, or any career, any path, any academic major that is heavily math related. Okay, because your kinds of application you will be working with out there in your future career will involve a lot more complicated functions. So allow me to, in this particular add-on, or we can call it a third part of the lecture, let's go ahead and look at some more complicated function. Okay. All right. So let's continue with example 5 right here. So here we are at example 5, and for the rest of these examples, they're all intended to be just indefinite integral problems like that, because you have already seen that once we are fluent with that skill of using substitution in finding an indefinite integral, then using substitution to find a definite integral is a lot easier. It's just a matter of we changing the integral bounds. So here I'm mostly going to focus on indefinite integral problems. So example 5, and we want to evaluate. All right, and so now students who are on track to a technical career, or engineering major or math major, and this is where you're seeing these functions, the trig function. So throughout the whole lessons earlier, both part 1 and part 2, we haven't had a chance to be exposed to any of the trig functions. So let's see how substitution methods can also be used quite effectively in your substitution, in your trig functions. Okay, so now I'm gonna look at, and this is also the first time we learn how to find the antiderivative of tangent. Okay, so now you have seen a few brief ideas earlier. If we are finding the antiderivative or the indefinite integral of a cosine function, then the answer simply is sine of x plus c, and simply because, how do we know that? Either we can refer back to that table I summarized earlier in the quarter, or we can just quickly take the derivative of this, and we will land of this sine of x plus constant c right here, we will land into the cosine. So that's the one of the basic one we already knew. And then we also knew that the antiderivative or the indefinite integral of sine of x would be minus cosine of x plus c. And once again, this was part of that summarized table I put down at the earlier part of the quarter when we were still looking at the very basic antiderivative works. And a simple explanation, taking the derivative here will land us back into that sine of x function. But then back then, these were about all we knew in terms of the antiderivative or the indefinite integral for all the trig functions. And when it came to tangent of x, sadly we didn't have any the particular problem, because there was no direct antiderivative up until what we were learning at that point. Okay, and so now with the substitution methods, now we are able to to actually proceed with finding the antiderivative for tangent of x here. So allow me, so we're definitely going to have to use some algebra here before we can take some real action, some real indefinite integral. So at start, we know by heart that a tangent of x is famously the ratio of sine over cosine. It's the fundamental definition of a tangent of x. And so this is not the integral yet. It's just a rewritten form of my starting function tangent of x. So tangent of x is written as a sine of x over cosine of x. And so now in that way, how is this falling in how will the substitution method that we're learning help to this problem? So I will go ahead and substitute, and according to what I've been explaining throughout the first two parts of the lecture here, then there are no right or wrong. But allow me throughout these examples, allow me to actually introduce my recommended substitution. And then as you follow along, you will start building your own experience, okay? So I recommend to substitute u with cosine of x. And it works, I mean, the way how it works here is almost similar to any of the problem we've had earlier in earlier parts of the lecture. We can just go directly with take this whole denominator here and substitute that for something simpler. Okay, and so that's what I did right here. I took that entire denominator and substitute that for an external variable u right here. So at that point, it's just a choice. I recommend it going this way, but you are more than welcome to reinvent the whole problem by choosing a different substitution. Okay, but the point now is that from this point on, we remember a couple checking points, right? Now, once we made that substitution, then, okay, I'm going to leave that a little bit aside now. The denominator will become a u, okay? And cosine of x did not get a substitution, it stays the same. The dx did not get a substitution, it stays the same. And so the question that I brought up earlier in the earlier part of the lecture, did I wash away completely all of the x variable? And apparently I did not. And that's why here in this part, consequently, we're going to go, so if u equals cosine of x, then the derivative du dx, okay, the derivative of u as a function of x is going to be minus sine of x, okay? And then so we also learned, up to this point, we've learned that so the du dx here, they're aside from being a fraction, it also means it's a fraction, it's a ratio of the two differential du over dx, and I've given all that explanation all over. And so now I can rearrange this, seeing this as a fraction, I can rearrange this as a du equals minus sine of x times dx. And furthermore, I can solve for the dx as a separate differential by dividing both sides by the minus sine of x, okay? And so consequently, I'm looking at du over minus sine of x will equal dx, okay? Du, the differential du over minus sine of x equals dx. And so in that way, now I'm ready to get back to my halfway done substitution problem right here. So according to the current substitution steps that we're doing, so we already substituted u for cosine of x. That's how we produce this, okay? And now it's just now realized I had a little bit of typo here. It was not meant to be a cosine, it's meant to be a sine of x here. And that sine of x did not get a substitution for that. Okay, so sine of x here in this problem still remains without a substitution. The denominator is a u, but now all that work here gives us all of that work there gives us a substitution perfectly good looking for the dx. So now the dx can be substituted by du over minus sine of x. All right, and so just how it comes together with the previous understanding in the two parts of the video lecture, then these two sine of x cancels and leaves behind a negative 1 factor. I can now bring that negative 1 factor in front and treat that as a negative expression. So now it's a negative 1 over u du. All right, and so at this point, this is a well-recognized function right here. I mean, well recognized in the sense that we already knew by heart what the antiderivative of this function is. And so that is giving me now negative natural log of u, but in absolute value, plus c. Okay, so we will never forget the plus c right here. And then on top of that, we have to make sure we bring back the original variable. So u was u substituted for cosine of x. So that means our function here is our final indefinite integral minus logarithm of cosine of x in absolute value plus c. So this is one answer for that. Okay, and so this problem in part A I brought up actually at the end of the problem here. We did not only solve the problem, but we also found a formula worth to remember. Again, I will never force any of my students to remember anything, but the more we work on this, it will stay. Okay, so for now, it will become a quite common formula, a quite common understanding. Antiderivative of tangent of x now officially is negative natural log of cosine of u, and I mean x, in absolute value plus c. This is a formula. Okay, we did that ourselves as a problem, and now this kind of problem happens often enough that people eventually will remember that as a formula. But here's the thing. There are quite a few mathematicians and math instructors out there don't like as a formula, they don't like having a negative sign in front of the formula. Okay, so here's another way that we can algebraically, so as far as the answer, we have found the answer to indefinite integral for tangent of x. Okay, but I would like to point out that some instructors and some mathematicians did not like that negative sign. So the property of logarithms, and recall that this negative sign means a negative 1 factor times a logarithm. And so now just a quick little algebra right here. Just that negative logarithm of cosine of x in absolute value, we can utilize the property, just the property of logarithm, to bring this negative sign as, so now logarithm, no more negative sign, it's positive sign in front now, but it's cosine of x to the negative 1. Now I actually write to the negative 1. I did not write cosine minus 1 of x to avoid the misunderstanding that this is an inverse function. Nope, it's not. I meant that it's cosine of x being raised to negative 1, because I understand usually if it is a cosine of x but raised to a power squared, then we usually write as a cosine squared of x. But in this case, I avoided doing that, okay, because I'm trying to avoid the misunderstanding that this is an inverse cosine of x. Nope, that's not. We want to raise cosine of x to the negative 1 power. Okay, but so have a little thinking, a little further thinking. A cosine of x raised to the negative 1 power, and of course it's to the power of negative 1. It means it's the reciprocal. This cosine of x to the negative 1 power is the reciprocal of 1 over cosine of x. I mean, it's the reciprocal of cosine of x, which is mathematically 1 over cosine of x. So 1 over cosine of x is, in other words, this is the natural log of secant of x. And again, that is all in absolute value. So, ladies and gentlemen, indeed, as another quite common formula, aside from the one I gave directly here, then many standard calculus textbooks and calculus professors write the following as a formula. The antiderivative for tangent of x equals, okay, logarithm, the natural log of secant of x in absolute value, and plus c. And this has now become the standard formula that's written in many calculus textbooks. Okay, and so that's how we have solved for part A, and this problem now, this example 5 is starting to involve the trig function, where we can start utilizing our understanding of the substitution methods. All right, so I'm going to erase the board, and we're heading out for part B of the example. All right, so in part B of the example, let's evaluate the following. Okay, so how about an integral, the indefinite integral for, how about 3 sine to the 4th of x times cosine of x dx. Okay, I mean, all of a sudden you feel like you're being thrown into a very complicated problem, but in the end, actually, it's not as bad. And here's the thing: whatever that you learn through this particular problem, you can also apply that generally to another problem. What I mean is, this problem could have also been, it could have been, so there's a coefficient, could have been whatever coefficient a that is, but it could have also been a cosine to a power, okay, whatever power that is. But then there's also always a standalone. So here it was a cosine. Here in this problem I wrote on the board, it's a sine to a power, and then there's a standalone power 1 single cosine. So there's sine and there's cosine, but one of them stays a single, no power, I mean power 1, and then the other one is raised to a power. And so in that generality, so the same problem could have also been, you know, cosine is being raised to a power, and then the other function, the other one being sine is the standalone one. And again, standalone, I mean, it's just 2 power 1 right here. And then there could be some potential coefficient in front, whatever that is. Okay? And so, and that's some generality about this kind. But you will see this kind of problem again in a much more general understanding as we progress on through the quarter, because we will get into a formal part where we learn, we will get into a formal lecture where we learn specifically about the technique to handle all the trig functions, And so this one will be one among them. And that particular lecture there will be titled as the Trig Substitution. So we're not doing that yet, but we get a preview idea in this particular problem. So in this problem specifically, I will substitute u as a suggestion, as a high recommendation. I'm suggesting to substitute u for sine of x. So all that sine of x is substituted by the variable u, the external variable u. Okay, so now in that way, so immediately we can see that the integral becomes, and of course every single step that we're making that substitution, then instantly you can kind of think about that as instantly the function itself, the integral itself can start changing, can start being, you know, replaced by a new variable step by step as a progress. So slowly we can have 3 remains there, but sine to the 4th now will become u to the 4th power. The cosine did not get a substitution, leave it there for now. And the dx did not get a substitution, leave it there for now. And that's why this space here is always saved separate. So since u equals sine of x, then du dx, that derivative there, right now I see that as a fraction. In addition to seeing that simply as a notation for derivative, but du dx is a cosine of x. So just now I said this is now also understood as a fraction of the 2 differential du over dx, and I can multiply the dx to the other side. So du equals a cosine of x dx, and we can algebraically, because now it's a fraction, so we can algebraically work around with this fraction and purposely solve the dx expression here, the dx differential here for as an expression in terms of the du. So it's du over cosine of x. Okay, and then so now I am going to use this expression as a way to substitute for my dx in the current halfway done substitution. All right, so the integral now becomes 3 times u to the 4th. Cosine of x did not get any substitution, but the dx now is substituted by du over cosine of x. Okay, so du over cosine of x, and now all of a sudden we realize such a good usefulness came out for us. We can cancel that cosine of x away without worrying about finding a substitution for it. So now all of a sudden the integral reduces to 3 times u to the 4th du, and all of a sudden now it has become a much simpler the integral problem to be handled. So now that 3 right there can be left out front. Here we're looking at u to the 4th du. That's one extra step. Sometimes you can skip that step if you're fluent enough. Okay, and so now the integral becomes so here we are ready for the final integral. That's what I meant right there. So 3 over 5 times u to the 5th plus c. Okay, but that's not quite our final answer, because in our responsibility we need to bring back the original x variable, which was in the beginning substituted away for that u variable. And so now it is going to be a 3/5, okay, in parentheses, sine of x to the 5th power plus c. All right, and here we are officially at our final answer right here. And this is just this problem has its own specialty, but it's not well credentialed enough to be regarded as a formula. So we just put it in a box right here, and we're done with that. Okay, and so that's another problem where we use a substitution method effectively to handle a quite complicated looking trig function. Okay, the trig function here is a high power of the sine of x. It could have been the high power on the cosine of x, and then it has the other one. So in trig function there's always sine and cosine. So I call that it's a trig function pair. There's sine and there's cosine, or there's cosine and there's sine. So if it's a high power on the sine right here, then the other function, the other one, the cosine is in singular power 1. Okay, and I also brought up that the other scenario right there in this generality. All right. So now let's look at part C, another problem right here. All right, so in our part C, the function now starting to involve a little more than just a trig function. So how about 2 e to the sine of x, okay, e to the sine of x times cosine of x dx, okay, 2 times e to the sine of x times cosine of x. And of course, now anyone viewing this video at this point in the lecture, you're well understanding that it's times dx. Okay, and so allow me to introduce my recommended substitution. I highly recommend to substitute u equals sine of x. That sine of x right there is for me, I see it's a good candidate for being substituted away. Okay, so once we substitute that away, instantly the problem will become. So I want my calculus students to actually, my formal calculus students who are on track into a technical career to get into that habit as soon as you make one step, regardless whether you go any further, as soon as you make one step in a substitution, start partially substitute away your expression. So here I'm doing 2 e to the u times cosine of x dx. And that's what I mean by start. As soon as we pick the substitution, we can start partially substituting away our expression to keep reducing it. And then, of course, whichever we did not substitute yet, it's okay. It stays the same. And that's the reason why we need to continue hunting. And that's the reason why the question I brought up in part A, in part 1 of the lecture, that have we washed away all of the variables, the old variables? We have not, and that motivates us to continue deriving the substitutions further. Okay, and so it looks like obviously we still have the cosine of x here did not get a substitution. I mean, did not get washed away, because the x is still here. The dx is also still here. So it rings a bell that we need to go further. So du dx as the derivative, that is cosine of x. So in this way, again, we have done this many times. So seeing this as a fraction now, I can multiply the dx to the other side. So du equals cosine of x dx. And I can divide both sides by that cosine of x to solve for the dx. And now dx is indeed equal to du over cosine of x. So now I can use this as a good substitution for that dx expression in my current problem right here. And so in that way, here's how I'm seeing it. It's 2 e to the u. Cosine did not get a substitution. It's okay. Leave it there. Okay. Dx now is substituted by du over cosine of x. Okay. So at least we have not washed away completely all of the O variables yet because the x is still here. But we've got more u variable involved now compared to the earlier step. And so now, just like how I've been showing throughout all of my examples since the beginning of the lecture, we can cancel this away. We don't need any substitution for that. So now all of a sudden we realize the integral just simply becomes 2 e to the u du. And now this is our successful point in a sense that have I washed away completely all of the x variables? Yes, I did. Yes, I have. And so now I can, in one intermediate step, I'm going to bring the constants out front, the constant coefficient out front, and now it's simply just e to the u du. Okay, and so anyone viewing this video at this point, anyone learning calculus up to this point, viewing the video, you are well aware that the antiderivative or the indefinite integral for e to the u is needless to say, e to the u, but there's a coefficient 2 in front, and we're adding c to that. This is now. But then, I apologize for putting that box a little too early. Now in our final responsibility, let's bring back the original meaning of the u variable. So u was substituting for sine of x. So it's our final antiderivative or indefinite integral becomes 2 times e to the sine of x. All of that plus c. That is another problem, how we can find the antiderivative or how we can find the indefinite integral using substitution method. All right, so in this example 5, let's look at another one. And of course, again, I have to keep reminding any of my students that it is almost impossible for any instructor to cover all kinds of examples out there, and especially now you're learning about integral calculus. Usually throughout many colleges and university, they call this calculus 2, so your majority in math has even gained higher already. Start being as creative as you can, okay? And so you can also come up with your own style, your own way of substituting, and we only need the fundamental, and then whatever the substitution, you can choose your own substitution. So be as creative. You don't have to do that. My way that I'm doing that is not the only way. Okay, so be as creative as you can right there. Okay, and there will be a whole world open out for you. All right, so I'm going to clean up the board, and let's look at part D of the example, where I would like to bring up another example where another problem where you can see how substitution can be used effectively when we are handling trig function. All right, so now I'm looking at about part D right here. The integral of about 3 e to the 3x, okay, times sine of e to the 3x dx. And it could also be the same problem here as a generality. It could also be a cosine here. So for you to be aware, it could be a cosine e to the 3x. Okay, so just be aware of that extended generality of this particular problem right here. But now in the way how I'm seeing it, generally speaking, we have a trig function, and inside of that trig function we have an e to the 3x. Okay, and then so it's not only just trig function, and similar to the one we've done in part C right here, it's not only trig function, it's trig function and mixed with an exponential. Okay, mixed with an exponential. So now in this problem, here's my recommendation. I recommend to substitute e to the 3x. Okay, I recommend to substitute e to the 3x. And e to the 3x is right here. Okay, and so now in that way, immediately the integral will become, so just like how the style, how I have been breaking it down right there, then I have 3u for e to the 3x times sine of u times du. Okay, and so set, and I mean dx. Okay, and so sadly, so we've had most of it substituted, most of the x variable washed away, except for this dx, sadly. And so in that way, we need to go back to the substitution and find a substitution for the d expression here. And so now in that way, my du dx equals, now derivative of this chain rule says it repeats e to the 3x, but we multiply with 3 as the derivative of this inside like that. Okay, and so now really it's du dx equals 3 times e to the 3x according to the chain rule. And now I'm going to start rearranging the terms right here. So now actually, if we notice, it's all the flexibility once you are fluent with your algebra. Okay, the only calculus work is here finding the du dx whatever, and then maybe in this kind of class, in this kind of setting we're learning, then we learn how to take antiderivative. But that's the only calculus fundamental. The rest are all, you see, being able to substitute, it's algebra. And now further substitution. Right here. This is one way how I see it. Now, du dx equals 3 times e to the 3x. But isn't this e to the 3x already substituted by u right there? Okay, so we can write this as du equals 3 times u, and then I multiply at the same time, I multiply that dx to the other side, so 3 times u times dx. Okay, and so in that way, I'm going to divide 3u from both sides, on both sides of our equation. So here dx equals du over 3u. Okay, it's just all the algebra. So the more algebra you have at this point, the more algebra you still remember that you can still retain, the more algebra skills that you can retain, the better the smoother it is for your calculus learning. Okay, so now what's usefulness about that? I mean, what's useful about what I just did? So now our almost done substituted problem here. In the next step, it's 3u times sine of u. Okay, and the dx now is going to get substituted by du over 3u. And so here's the thing. Technically, as far as the substitution, we're done. Technically. Okay? But now we would like to even simplify our problem because, see, everything is already in terms of u. So we can start taking the antiderivative, the indefinite integral. But I would hold on to that. More algebra, a little more algebra, making life easier for us. Cancel away the 3u right here. Okay, and that now gives me sine of u du. This is one simple function to find the antiderivative for it, because we either use that as a formula, and we have seen that all over. And so now this is going to be negative cosine of u plus c. And then the only remaining responsibility now is to bring back the original substitution for u. So our final answer here is a minus cosine of e to the 3x, okay, plus c. And that is how we are done for this problem. So before I'm moving out to the next example, okay, and so this problem right here is tentatively my last problem that I deliver in example 5, and example 6 and the later examples will cover a different class of functions like that. But they're all aimed at the purpose to give my viewers, my students, more experience in terms of using the substitution method to see how flexible you can use that. But then I should have always mentioned throughout any of the problems that we have done, take the derivative here. You can always go back to each one of my answer, because I don't want my video lesson to get too lengthy. So I highly recommend go back to every single problem that I've done throughout this example and throughout the previous example and throughout all the later examples. Pause the video at the final answer. take the derivative here to ensure that I have gotten the correct antiderivative. And of course, you gotta forgive me at some point that I'm just a human being as anybody else. I may make mistake here, and I never, and right in front of the camera, I never have a chance to check myself. Okay, so you're more than welcome to take the derivative here to ensure that I've had the correct antiderivative, to ensure that this derivative, the derivative of this, any of these final answers will land back into our beginning function in the integral problem. But even if I made error, even if you would find any error right here, it will not change the ultimate fundamentals on any of these problems right here. It won't change the generality of how we approach these problems. Okay? And now we are ready for example 6. And another example where I introduce a different class of problems where we can effectively use a substitution method to find the answer right here. All right, so how about part A of this example? Let's look at an integral as following. It's a rational function, 7x plus 2 over x squared plus 1. X squared plus 1 times the dx. Okay, so gosh, this problem looks so like a lot of those problems I've done throughout example 1 up until example 3. It's a rational function. But now if we look a little closely, now I gotta spend time a little bit on this problem, on a problem like this, so that you will understand the idea later that sometimes, the substitution sometimes will not come out as trivial as it used to be. Okay, there are problems where yes, we will use substitution method, but it might take some creativity. Okay, and so usually, according to the problem we have done previously, then that many people in the experience that you have learned through the previous examples up to example 3 in the earlier part of this lecture, then you might think immediately that u equals x squared plus 1. To substitute for that, there are no right or wrong substitution. I'm not against that. Feel free to try that path right here. The idea is for any substitution that you have chosen, you got to ensure to yourself, will I wash away, or once you made the substitution, you have to check yourself, did I wash away completely all of the x variable? Okay, and so in this case, I'm looking at the du dx to be a 2x, and then du divided by 2x, rearranging this relationship here, we're looking at du over 2x equals dx. And so the substitution here quickly can become, and if you could follow along with this particular work here on scratch paper, okay? Because I just want to point out, some struggle, some difficulty with some problem that where we need to start putting in some creativity. And so right now we follow with things that we are familiar with. Okay, we are following with things that we're comfortable with, and then we're gonna face some struggle, some difficulty, and then that forces us to look for some other creative solution like that. So here, if we're going in the direct substitution, pick the whole denominator here, and like how I've been doing it, okay, like how I've been showing in past lesson, then 7x plus 2 did not get a substitution for that, and then here it gets a substitution. We found a substitution for the dx, which is now become du over 2x, but now sadly there is no way to cancel, and that's where we're facing difficulty. So in other words, yes, the substitution is still going, but then we got hung up right here without being able to deal with that remaining x right here. Okay, and that's why I'm not saying that it's a dead end here, but there could be students who are super brilliant in mind and know a way to handle past this point, but I officially tell anyone watching this video, I'm stuck here. Okay, and this brings a good sign for me to move on to look for some other solution. We're still doing the substitution, but hey, maybe substituting the entire denominator here was not a good plan, maybe at least for me. Okay, and so now let me point out that, and that will once again emphasize my explanation earlier that there are no right or wrong substitution. It all it all takes some creativity right there. Okay, and so in this case, I actually will first, in this problem right here, I will have to do a little bit of algebra. I'm gonna, notice the nature of this problem right here, that having two terms in the numerator. And so I am going to break the problem down into a 7x over the x squared plus 1. That's one integral. And then the other term is the integral on 2 over the x squared plus 1 dx. Okay? And so the substitution we chose earlier, it didn't work directly in the problem, but see now before, and maybe what I said earlier about being a creative here, this is where we can be creative a little bit, okay? And I'm not even sure about what we should choose for the substitution yet, okay? But now at least algebraically I can break this problem into two separate terms like that. Two separate terms. And so now, sadly, we have to handle this problem as two separate little problems. So now for the first problem there, then I can substitute. And so I'm only substituting this u for x squared plus 1. So yes, again, I substitute u for x squared plus 1. And this is now how I see it. Yes, all that du dx will be 2x. Okay, and then du divided by 2x will equal dx by rearranging this equation. And of course, we are already well aware that this is now a fraction of the two differentials, du and dx. But now I'm specifically just looking at the first integral right here. So the first integral there is going to be a 7x without substitution. It's a u here. The dx now becomes du over 2x. Okay? And then just that one there. Now the x here can get cancelled, and then we have a 7/2 here as a coefficient. Or in other words, okay, I can leave in the next step, I can leave the 7/2 in front, and this is a 1 over u du. That's just the work for this particular integral. But then we still have the other one hanging out there. The integral of 2 over the x squared plus 1 dx. So now to let anybody know, 2 here really is just a 2 times 1. This is a 2 times 1. So I can rewrite that here as a 2 times 1 over x squared plus 1 dx. So in other words, the substitution I did, it's not a direct substitution for the whole thing here, but the creativity here first is that I broke it down into two separate ones, and the substitution I only used that for the first piece. Okay? The second piece remains pretty much the same, and I'm just leaving it there, hanging there for a little while. 1 over the x squared plus 1. At least that's how I'm doing it. So two separate, and keep thinking of that as two separate works, and once, so in every step, this second integral here remains the same in every step until we're completely done with the first one, and then we're going to turn our focus to the other term and complete our work. How's that? Because in the end, we're just having two separate works, and no one can do two works instantly at the same time. There has to be one before the other one. So I chose to go with this one before the other one. It's just making sense that way naturally. Okay, and so now this first integral here in my next step, 7/2, and that becomes a natural log of absolute value of u. And we don't need a plus c here yet, because I'm going to put the plus c at the very end when we also have found the antiderivative of this term right here. But see, mostly, as I said, in the first many steps, I'm focusing on the first integral here. And so that's 7/2 times the natural log of u in absolute value. And then the second integral remains the same for now, without being done. Okay, and so now in my next board, over to my next board, the first integral, we are now required to bring back the original substitution for the u variable. So now it's going to be 7/2 times, and I don't think, we don't need that integral sign, natural log of the x squared, absolute value of x squared plus 1. So we are now done with the first term in our integral, the first term of our integral. And now it's a 2 times 1 over x squared plus 1 dx. So it's now a good sign telling us that it's time to move on to the next term, finding the integral of the next term in the next step. Okay, and so just a little bit of scratch work, but to remind yourself, does anybody recognize this? So now I recall this integral right here is simple, and it's just one thing to remember. We've seen this in the beginning of our learning, our quarter, learning about this is a tangent inverse of x. When we were beginning learning about antiderivative, we went through this, and this is just one pretty formula. I mean, pretty easy to remember formula that it's directly came out from calculus integral. I mean, differential calculus that we've learned previously. Okay, because derivative of tangent inverse is 1 over 1 plus x squared. So now taking the antiderivative or indefinite integral, it's just going back to tangent inverse. So what's the usefulness of recalling this quick little formula? That's what this is. Okay, so 1 over x squared plus 1 is just a rewritten form, a rearranged form of this 1 over 1 plus x squared. And so now, in other words, all of a sudden we only need one extra step. First term now is done, which will remain the same throughout the many steps remaining, or just maybe one step left. The coefficient is 2, but now it's tangent inverse of x, and we don't even need to do any substitution for that. Okay, and so now we can legally put a plus here. That is how we have done. We have finished our particular problem here. And so it took me some time to explain and all that, but then the generality I would like to point out in this kind of problem is that sometimes the substitution doesn't come so directly. You will need to do some algebraic breaking down of your integral, and usually it happens in a way that, you know, your integral here in the numerator, I mean, you got a fraction here, and then the numerator has multiple terms. We can take advantage of that and breaking it down into separate terms, and then each separate terms, each of the separate terms right here will be handled separately with a different approach. Okay, so for example, the substitution will happen on the first term, but then the second term comes just simply as something we already knew. Okay, and so now in that way, I am erasing the board and introduce the next part of example 6. All right, so part B. And the problem I have here, let's look at how about the integral, okay, of x minus 1 divided by square root of 1 minus x squared, the dx. Okay, and so now, along with that expression, allow me to not beating around the bush too much. If we directly work on this and choose a substitution 1 minus x squared here, it will work. It will work, but not immediately yet. Not immediately yet. Okay, it will work, but not immediately. And so du over dx will be a minus 2x, and consequently that will bring du over, after rearranging, du over minus 2x to equal dx. So we can partly see, I mean, we can see that it doesn't quite work yet directly as a substitution into this problem, because x minus 1 did not have a substitution. And then here in the denominator, we can write it as a square root of u, and the dx can be du over minus 2x, but that's about it. We can't cancel this minus 2x directly with that x minus 1. We can't cancel that away. And so now in that way, picking up from the experience we have had, and this work, according to what we have seen already in part A, this work did not go into the trash. It did not become a waste for us. Okay, it's still usable, but just how do we use that correctly? How do we use that to bring good results for us? So the first step before I'm doing any substitution, I'm breaking this down. See, we got two terms in the numerator. I'm breaking this down to x over the over the square root of 1 minus x squared dx. That's one integral problem separately. And then I'm going to subtract, and then the next term here is, so the subtraction sign came out because of that negative sign, because of that minus sign, and then subtract 1 over square root of 1 minus x squared. And I just realized I wrote my two terms a little too close, so I ran out of space. 1 over square root of 1 minus x squared, again with the dx right here. Okay, and so now I am going to still use this substitution, but only for the first integral. And in the end, again, just like part A, we have two separate problems to handle. This one here needs to be handled later, or if you want to start out with this one first, that's fine. Or maybe in this time, in this problem, let's start out with this, this second one first. So I'm going to leave this one here the same for now. Okay. So x over square root of 1 minus x squared dx. Just want to try out different directions. Okay. Even though I already had a lot of steps getting ready for this integral, but we don't have to always immediately go that route. See, if we recognize this is sine inverse of x, simply just that. Okay, simply just that. And I'm holding on to doing the plus c here, okay, because I want to wait until we completely get that antiderivative, and then we do the plus c at the end, because this gives us a constant that already gave us a constant. There's two constants added together, so why not just wait until the very last step and put an overall constant? That's the plan right there. But see, as a reminder, see, derivative of sine inverse is 1 over square root of 1 minus x squared. And that's the reason why now taking that antiderivative gives us back to that sine inverse right there. We've learned this back from, usually we call that calculus 1, but mainly it's differential calculus, the calculus you learn about derivative. And then now integral calculus, we're going backward, finding antiderivative. Okay? And so all of a sudden, it's only one step that we already found the answer to the second integral. That's why usually I leave it there for a little while, and I tend to handle the first one that's slightly more complicated, that really needs the substitution. All right, so now let's let the substitution kick in. And recall again, I'm only substituting for this part right here. And so now the substitution can partially be done as following. X did not get a substitution, so what? Leave it there. Square root of u, okay? And all of a sudden, the usefulness here is that the expression inside the root has already been so reduced, okay? And then the dx now is substituted by du over 2x. So, and I mean over du over negative 2x, okay? And so the x will cancel out, okay? And the minus 2 will be eventually brought in front like that. But then don't forget, we already had the next term being finished. So I'm going to leave it there. And we don't need to, remember, there's no integral sign here, so we don't need to handle that any longer. This term will remain with us for the rest of the later steps. Okay, so now I'm going to move over to the other board of mine. All right, so now the first term of the integral, the remaining integral becomes just a minus 1/2 1 over square root of u du, and then subtracting the remaining term, which is already done. Okay, and so now this particular integral right here, think of that as a one. How about one more step? Think of that as a u to the negative 1/2 power to the du, and minus sine inverse of x. Okay, and so in the next step, it is simply just a negative 1/2 times a u, and now we're getting that out of the integral sign like that. U to the, so negative 1/2 plus 1 is going to be a positive 1/2, but I'm going to have to divide that by a positive 1/2. So here I can just use the simple power rule. Okay, and then minus sine inverse of x, and so that 1/2 will cancel with this 1/2 right there, and we'll leave behind the negative sign. So in my next step, it is minus u to the 1/2 power, okay, minus sine of x, and I mean sine inverse of x right there, and then plus c. But now don't forget, we need to bring back whatever the meaning, the substitution the substituted expression that u substituted for. And so that will be minus, okay, 1 minus u, and I mean x. 1 minus x squared, okay, to the 1/2 power, and minus sine inverse of x plus c. And that's how we're done. Okay. The same final answer here, you can alternatively express that. You can alternatively express that if you like to, if you would like to, or in case any of your instructor aside from me require you to, then you can put this in square root form. So minus in front of the square root, minus square root of 1 minus x squared, okay, and then minus sine inverse of x plus c. That's another way of expressing the final answer. Those are the two exact same answers. Okay. All right, and now we are ready for example number 7. And again, another example where I introduce a different class of integral problems out there. Okay, and so let me now write down part A. So let's evaluate the integral of eta x over x to the 4th plus 1, okay, dx. All right, and so this one right here, immediately the direct substitution will not work. And or at least it doesn't work for me, and that's why, it motivated me into hunting for different solutions. So here's the thing, let's try out the thing that we usually do, that we're comfortably do. Normally or usually we pick the entire denominator, because again, observation is telling us that this is a rational expression. So usually, and throughout most of the examples or all of the examples I've done in lecture part A and part 1 and part 2 right there, then we have been picking right from the whole denominator, okay? Or sometimes the denominator but inside the power, but here let's pick the whole denominator. So going that way, will it work? Or at least for me, is it going to work for me? So here we have 8x divided by u, and then with the dx, and again, I recommend that this work here for any of the viewers and students of mine to keep this work here on scratch paper right now, because I just want to point out at some point the direct substitution will run into some struggle, at least for me, okay? And so du dx, the derivative of this substitution, will equal 4x cubed. That means du over 4x cubed is going to equal dx. Okay, and so, but then here's how I see it. When we're substituting this into the function, then we have 8x, and x remains the same, did not get a substitution for that. The u in the denominator already was a substitution. Dx here can be substituted by du over 4x cubed, and yes, some cancellation happened, admittedly. And then we're running into a 2 times a 1 over u times du over x cubed. So we're still, and I mean x squared after the cancellation. So we still got hung up here with that, unresolved old variable. We did not completely wash away, okay? And so we got hung up here, at least for me. I got hung up here. So I'm going to roll back and think about the way we usually do right here. So if we look back at the way how we approach in earlier problems throughout up to example 3 and even example 4 like that, in the earlier part of the lecture here, then usually in those problems, think about the cancellation part is this part where because once we made that substitution, then we want to eventually some cancellation to happen. But then we want to substitute in a way that, you see, so the 8x here, that eventually if I aim to cancel that away, to completely wash out all the variables, then the substitution has to be something but in the form of an x squared power, 1 power above that. So that when we differentiate, when we take the derivative, okay, it's going to give us some coefficient with the with 2x. So it's a power 1 here that matches with that. Okay, take a moment, pause the video and try to understand, or you can keep rewinding the part I just said right there. Because according to the work I've been doing throughout all of that example, up from 1 up to example 3, right there, it looks like I led people into the understanding that we try to aim, the part that we aim to cancel away, then the substitution usually happen in a way, that the power of the substitution is 1 degree higher than the power that we are aiming to cancel away. Okay, and so, but here if we substitute like that, then obviously the power was a little too high for the x squared, for the 8x here, so it didn't cancel away. And so if we now stay with that idea right here, is there a way to recognize the power 2 among this expression? So apparently this substitution did not work out. So that's why in this way, after you have paused or maybe rewinded the video quite a few times to understand my explanation just now, then I would. So once again, I'm looking for to substitute u as something that involves the x squared right there, so that when I take the derivative, it's degree 2. So when I take the derivative, it goes back to degree 1. Okay, and so here's how I'm seeing it. The 8x is there, of course, and that's why it caused trouble, because it caused trouble with the x to the 4th. Here, the derivative of x to the 4th, it doesn't give me just x. I see the x to the 4th here as x squared plus 1. Now have a minute to think about what I just re-expressed right there, and what usefulness will it bring for us. Okay, because didn't I just say earlier, in order to find way to cancel away this x right here after the substitutions, I need the substitution to take on some form of being a second degree, a power 2 right there. Okay, a polynomial power 2 somehow, some way. That one is now a well-qualifying candidate. Now I'm going to go ahead and substitute u for the x squared right there. Okay, and so in that way, du dx is a simple substitution. Will be 2x, and I didn't even have any coefficient in front of that. I just had, because it came right out from here. Okay, and so now du over 2x will equal dx after rearranging this equation right there. And so now we can start partially substituting away our expression. 8x did not get a substitution. It stays the same. The x squared here is substituted by u. So your overall expression in the denominator becomes u squared plus 1. Okay? And dx in the meanwhile now gets a substitution for du over 2x. Now the substitution allows us, with this style of substitution, it allows us to completely cancel the x. You see, chosen a power 2 for your function ready for substitution. After the derivative step, it will somehow cancel, and it matches. After the derivative, it matches the power with this 8x right here, and that's the one that we intend to wash away. Okay, and so. And then 8 cancel with 2 gives me a 4 as a coefficient in front. So now our integral reduces down to a 4 times the integral of 1 over u squared plus 1 du. All right, and I mentioned this in the earlier problem here, right here within this part 3 of the lecture, in some of the earlier lecture. Some of the earlier example. This is going to be what? Tangent inverse, right? The antiderivative of 1 over u squared plus 1. And so now I'm looking at 4 times the tangent inverse of u plus c. But then we are required to bring back the original variable substitution. And so our final answer here is going to be 4 tangent inverse of x squared plus c. And that is the expression that I'm looking at. That is the final answer for our problem. 4 tangent inverse of x squared. Okay, and so once again, feel free to roll back to that video of mine and then continue watching the next problem so that you can start getting the idea that, so at this point, a substitution can start being you can start being creative in terms of choosing your substitution. But so far I've been maintaining that idea that the substituted expression, once we substitute it away, it has to leave us a door to cancel away the part that we did not substitute for, or we could not substitute for. Okay, because once we chose a substitution, then we will definitely get some substitution for the dx expression, but then it will still remain with some remaining old variable. So that has to be somehow matched with the beginning variable so that we can cancel that away. We can wash that away. Okay, so make sure you choose a substitution at the bottom line here. Make sure we choose a substitution that leaves us a door to cancel the part where it did not get a substitution. Okay, so that we can cancel that away and eventually turn our expression, our integral problem, before we can integrate that, right? Turn our integral problem into something that's completely in terms of the new variable. And that's why I keep, right from the first the moments introducing about the idea of substitution, I keep emphasizing that question that you got to ask yourself, did I wash away the old variable completely? Okay, and so now part B, allow me to bring in part B of this example 7 as sort of like an extension of this part A we just finished. All right, so here part B, we're looking at an integral of 4x cubed over about 20 x to the 8 plus 5 with a dx. All right, and so now so just along that way right there, then again just a little bit of a planning right here. See, if we if we substitute the whole 20x to the 8 plus 5 in the denominator for a u, then our du dx, our derivative there, because if we substituted this for u, then of course that did not get a substitution, right? And it's power 3 right now. And so, in the way I'm seeing this, after we take the derivative here, it gives us 160x to the 7, and that constant term is gone away, so it won't cancel too nicely. So we're still going to have some left over the power of x. And so we definitely don't want to go that way, but instead we want to choose u to be something. It's power 3 here. So we want to pick a u so that it's going to be somewhere to the 4th power, whatever coefficient in front. It could be fine. But we want a u to be substituting for the 4th power, because when we take the derivative on the 4th power, we're going to end up into the 3rd power, which will cancel with this. All right, and that's the plan right there for that. And so now in that way, but we still don't see things too clearly. If we immediately rewrite, or how about let me approach things this way. So now in that understanding, this problem is similar to the earlier problem, but in the sense now that each of the power here has some crazy coefficient, and then there's a constant term. So algebraically, the next step I'm doing here, I'm still going to leave the 4x cubed here, but I'm going to factor out the 5 right here. I'm going to factor out the 5, okay? And then that gives me 5 times, okay, in parentheses, 4x to the 8 plus 1 dx for a good purpose later on. So I start displaying the plus 1 here to make it similar to the problem we've had earlier, and now 4 over 5 can be regarded as a coefficient in front of our integral problem. So here it's just simply x cubed, and now it's 4x to the 8th plus 1 dx. Okay, and so now we're almost there. So yes, at this point, a lot of people start thinking about making u equal simply x to the 4th, so that because 8x to the 8, you can see that you can start seeing x to the 8 along with the experience you have picked up from part A of this example. X to the 8 can be regarded as x to the 4th. We got what we want right there, almost, okay, and square, but let's be a little more than that. So here's the thing. For this problem, because this was good when it was single term here, and I mean coefficient 1, but now it's coefficient 4, so let's do something let's do something a little bit more clever over here. I'm going to observe the 4x to the 8, the whole 4x to the 8 as square, actually 2x to the 4th. Okay, 2x to the 4th, but being raised to the square power algebraically. I'm seeing 4x to the 8th as 2x to the 4th square. Okay, and now, so we still got the 4th power, but it's going to have additionally a coefficient in front. Okay, and so now doing that, it will completely turn this into one u term, so that we don't have to worry about all of the other fancy coefficients, which is probably making things harder for us. And so now my substitutions, I'm a little more firm. But in the end, it's not a right or wrong. Just whatever we choose here, we did a little shopping plan, okay? But then there could still be a different ways of shopping for a good product. You see what I'm saying now? So this way I'm going here is not the only way, okay? It's just one of the substitution I chose with some planning, and then if it still doesn't work, we're gonna find a different one again, okay? So now I'm substituting u equals 2x to the 4th. All right, and so now as I'm substituting that, and here's what the problem becomes. 4/5 as a coefficient in front. X cubed did not get a substitution, it stays the same. The 4x to the 8 right here is substituted as u, completely u to the square power plus 1 times the dx. See how nice it reduces right there? Okay, just write on that, the substitution. Okay, and again, just make a note if you have to. This thing here, I'm seeing that as a 2x to the 4th, but all square, and that's why I made that substitution as a decision. Okay, and so, but in the end, it's, again, I keep saying it's not a right or wrong substitution. No one should take points away. I mean, no one should judge you on making a right or wrong. If what matters, will it make it work? Okay, and so now from this substitution, I'm going with a du dx equals 8x cubed. And now I'm starting to display that cube power that to match with that. So some good, something still going with the plan. That eventually I want to cancel that away. Okay, completely. And so now du over 8x cubed is going to equal to dx. Okay, and so now allow me to erase this little note now. So to continue with the problem, now I'm looking at 4/5, okay, and then the integral of x cubed stays the same for now, just like that. It didn't get a substitution, let it be there. And then u to the u squared plus 1, but dx now is substituted by du over 8x cubed. Du over 8x cubed. And so now gladly the x cubed will cancel, the 8 will cancel with that 4, and be whatever remains as a factor can be brought in front. So now we're looking at 1/10. The integral of, with the integral of 1 over u squared plus 1 du. Okay, so two problems eventually we want to make our way. This problem in part A, we eventually want to make our way into expressing things as a 1 over u squared plus 1, so that we can bring it into a tangent inverse. Okay, but that's just, something. But in the end, I want any one of you viewing this video to treat these problems as problems that build your confidence and that keep giving you more experience right there. But that should not limit your own creativity. Okay, and so here you got a 1/10. Okay, and then now it will become tangent inverse of u and plus c. But now I'm going to need the next board right there, the other board, to finalize my final expression, because we are required to bring back the original substitution for this. Okay. All right. So now on this board of mine right here, so from the previous step, 1/10 tangent inverse of u plus c. But now recall that u equals 2x to the 4th that I substituted previously. Okay, so now this answer here will become 1/10 tangent inverse of 2x to the 4th plus c. And this is our final answer as the antiderivative or the indefinite integral for that crazy looking problem in the beginning. 4x cubed over the 20x to the 8 plus 5 like that. Okay, so two problems that I try my way to bring that into the tangent inverse, or brought it into this form right here. Okay, and so you can probably also pick up some other experience along with what I was doing, even though I may not have said that. Okay, so still in example 7, let me now erase my board and let's look at a different problem. In part C of this example, let me introduce the integral, and of course for any of the problems that I put in the same example, that means they do have some similarity. So I want my students, or I want viewers who view this video, to carefully roll back to each problem in one same example to recognize for yourself some details, some other common things among these problems that maybe I missed, and I didn't have a chance to mention that in my lecture here, in my video lesson here. So here I'm looking at x to the 6 divided by square root of 1 minus x to the 14 dx. Okay. So this one is another one that's very similar to the very first one and the second one, in the sense that, you see, if I substitute the whole 1 minus x to the 14 for u, this is now completely scratch work. du dx is going to land into a minus 14x to the 13. So as far as planning this, I have a high sense that it's not going to work too well, because the power that remains after the derivative is too high. So when we substitute that back for this dx right here, it won't cancel. I mean, it will cancel, but it's still going to have some remains of the power here. So we're still stuck with some x variable, completely unwashed. Okay, that's still there. So remember, the point is we do whatever substitution, but we got to ensure. So substitution is not right or wrong, but you got to ensure your substitution can wash away all of your old variable. That's the whole point right there. So doing this route here, now I have a high sense that it's not going to work too well. So rather, I choose, think of this. If I want to wash that away completely and nothing else left, then I want I want u to equal some coefficient with x to the 7. Some coefficient, that's what the dots are, okay, with x to the 7, because the derivative on the x to the 7 is going to be at least something that involves the x to the 6. Okay, some coefficient that involves x to the 6. Or maybe let me be a little more precise, some coefficient times with 7x to the 6. But this primary x to the 6 will be canceled nicely with that x to the 6. So that's the plan right there. All right, so now, so plus on top of that, I do see the x to the 14 in my expression can be written as x to the 7 square. Okay, so that can bring a good sign for us. All right, so that's why in this way, now I'm more firm. But in the end, I'm only saying I'm more firm. That plan could still fail. Okay, so there are no right or wrong. It takes me a lot of time to practice on any of this. And then my time back then when I was in college, when I was in the early years developing my own calculus study, my calculus experience, I spent a lot of time working on these problems. There's no, overnight waking up and be good at these things. Okay, you just have to keep learning and learning. And so u equals x squared. That's what I chose for now, for simplicity. Okay? And so partially the problem will become, here, let me correct that, u equals x to the 7. Okay, in my mind I was thinking about the square of the x to the 7. So partially the problem becomes the integral of x to the 6. So x to the 6 stays the same because it did not get a substitution. But now in the denominator, I'm rewriting this square root expression as 1 minus u squared, and with the dx. And again, all because of what we notice here is x to the 14 is the same as x to the 7 squared. So I substituted that. And all I'm saying is at this point, I'm more firm about I should choose that one, but I can still never guarantee will it work perfectly. It all depends on how we go. Okay, so in that way, let's continue. Once I chose u equals x to the 7, then du dx will equal 7x to the 6. Okay, so it looks like there's hope here. Okay, so x to the 6 does look matching with that. It does look to match with that. And so du over 7x to the 6, after rearranging that equation here, will equal dx. And so now in that way, I'm looking at the integral in the next step. After some more substitution, will become x to the 6 over square root of 1 minus u squared. Okay, but the dx now is completely substituted by du over 7x to the 6. And now it looks like we're so close to some good victory right here, because now we can successfully cancel the x to the 6 away and bring that 7 as a 1/7 to the front to become a coefficient. So now I'm looking at the 1/7, okay, integral of 1 over square root of 1 minus u squared with the du. All right, so now what good is this? This is recognized as, 1 over square root of 1 minus u squared itself is recognized as the inverse sine or sine inverse of u. Okay, arc sine of u. Textbook can also write that way. So now this problem turns out simply 1/7 as a coefficient, sine inverse or arc sine of u. So many textbooks also write this as arc sine, okay, of u, or arc tangent for tangent inverse, and so on and so on. Allow me to not be too worried about these optional explanations where you can always find them easily over the web and all that. Okay, and plus c. And now it's just the last step where we are required to bring back the original x variable right there. So in that way, my final answer now is going to be a 1/7, okay, sine inverse of the x to the 7 plus c. And now we've had our solid answer for that. Okay. And so now let's bring up another problem in this example 7, where it has some similarity with part C that we just now finished. All right, so part D of example 7. I'm looking at, how about 2 over square root of 9 minus 25 t squared dt. All right, and so I don't see an x here. And that means I am going to choose a substitution somehow, so that, and without seeing an x, maybe I should bring the 2 in front right here to leave it completely a 1. Okay, and then there's a 9 minus 25 t squared here with the dt. So I want to choose, so this 1 right here, it's a constant. Okay, so I want to choose, and it also means t to the 0 power. That's what the 1 is. 1 means t to the 0 power. So I'm trying to get direct into that planning, because we have seen tons of these, enough experience throughout this whole example 7. So that means if we choose a substitution, maybe it's a good idea to choose the t so that it goes to the just u equals t, power 1. Because our t here is the power 2, we don't want to get that. Because if we chose u equals t squared, then we're going to get stuck with du dt to be just a 2t. We're still going to have a t, but our problem don't have any t in the part that we want to cancel away. So we want to choose the u so that it's power 1. Power 1 here, so that when you take the derivative, it's going to become a constant term. Okay, so keep that as a plan right there. So now I'm going to be more firm that I'm going to take something with u, some coefficient with u, u equals some coefficient with t to the first power. But now before I even proceed with that and rushly, before I can rushly choose a u equals t, okay, too simple, then here's the problem. Here's what I'm seeing. Why don't we factor out? I mean, this problem right here, we have fancy terms and fancy coefficient. 9 as a constant term inside the square root minus 25t squared. So the t squared get a coefficient. So why don't we factor out completely the 9 right here, okay, in the square root. And that leaves me 1 minus 25 now over 9 t squared. So in the square root, some fancy thing happens right there. But now it's a product between 9 and this, 1 minus 25 over 9 t squared. Algebra again, okay? And I have a purpose why I'm doing that, and hopefully you will pick up a little trick here and there along with what I'm doing as well. All right, so I can break that out of the square root and turning that into a 3. So now I'm looking at the 2/3 times the square root, I mean the integral of 1 over 1 minus 25 over 9 t squared, okay, in the square roots, okay, dt. All right, and so now I can see, now this term right here, I'm going to give another hint right here. 25 over 9 t squared can be thought of, can be regarded as 5t over 3 all squared, okay. Pause my video. Go ahead and pause my video if you need to algebraically verify yourself about this. Okay, but now once I've pointed this out, this is where I'm firm about what I should choose for the u right here. U should be, I mean, u is firm for me, and if it doesn't work, I'm going to have to try again. Okay, 5/3 t, that's my u. And so now in that way, right after I chose my u, then partially this will become 2/3, okay, the integral of 1 over square root of 1 minus, all that here now is a u squared, okay, dt, but we're still stuck with that dt. And once again, how do I see this as u squared? Because see, I just pointed out earlier, 25 over 9 t squared is really the same as 5t over 3 all squared. That's why I have now it's u squared here, because u is substituted. I mean, u substitutes for 5 over 3 t, okay, 5/3 t. And so now in that way, we got the problem partially substituted away, but we still have that dt remains, right? So now that means my du dt right from this substitution is going to give me just simply a 5/3. Simple derivative work. And so now du, and so I can rearrange this to get 3/5 times du to equals dt. All right, and so now that I hope no one needs me to give extra clarification on that, because it's just the algebra for rearranging that, and we purposely want to rewrite that equation so that we can express dt as an expression involve du right there. All right, I'm out of space, so let me move to the other board. So with the integral that's almost completed with all the substitution, we're looking at 2/3, okay, and then 1 over the square root of 1 minus u squared, and then the dt now is going to be substituted by 3/5, okay, 3/5 du. All right, and so now we have washed away completely all of the all of the t variable, and just have left behind remaining here with all the u variable. I can also bring that 3/5 in front, making it, so now the 3 cancel with that 3, so now I'm looking at just simply a 2/5 right here. Integral of 1 over the square root now of 1 minus u squared, okay, with a du. And so now I can successfully see this as the sine inverse of u with the coefficient 2/5 in front. So now it is 2/5 arc sine or sine inverse of u plus c. But now we are required to bring back the original substitution, so the original variable. So now 2/5 times sine inverse of 5/3, okay, t plus c, and that's our final answer. All right, and now let's look at example number 8 right here. And in this particular example, I am going to be only bringing in one problem throughout the whole thing. Now, the reason I'm doing this because the kind of problem I introduced here in this example 8 deserves its own lecture. So, you know, the style of substitution method I'm using here, I'm introducing here is only as a preview right there. And then later on in the quarter, later on in the academic term, learning about integral calculus, I will have a separate video lesson, a separate video lecture about the kind of the style, the technique that handle this kind of integral right there, or this, at least this style of doing substitution. So for that reason, here the problem I brought up here in this lecture only serves as a preview problem where you can start picking up some good trick from here, okay? But I don't aim as too much detailed explanation. And then later on, as we get into the formal lecture where I talked about this style of being creative for your integral, then we can talk more about the details there. So example number 8. Now let me bring up. How about let's evaluate the integral of about 5x. Okay, times the square root of x minus 3 dx. Okay, this one integral. But see, simple, being simple, looking simple doesn't mean it's easy. Okay, and this problem sometimes being simple means it could be dangerous. So here, if we choose the usual style of doing the usual style of doing integral work, I mean, the point now is that we have quite a few different styles. We can choose u equals square root of the x minus 3. We can also choose u equals x minus 3. Okay, and then we definitely can do this, but it's kind of pointless because we're doing this. It just basically means the whole problem that's we change to a new variable. That's all. But it doesn't help us at all. And so for this problem, I highly recommend taking that integral. I mean, taking that substitution, u equals x minus 3. So I'm going to nail that down right here. Okay. We can do that. And then the other one can also work. The other one will also work, but you know, you can try it on your own time. And after this video, I mean, after this problem is finished, I can also point out a couple of directions with that. Okay, but now the idea, what's special about this problem? I just wanted to show you how flexible you can, or how much you can do with a substitution once you have made that substitution. Okay, and it's all about the substitution. It's all about the substitution, what we can substitute. So, right from here, then things look quite simple so far. Du dx equals 1. And so that means we can rearrange this to obtain du equals dx. And so then immediately the integral can partially be done by 5x. Now, x did not get a substitution. U was substituting for x minus 3. Okay, and so that's why 5x remains the same. But now it's a square root of u. And the dx immediately get that substitution for that, so it's now a du here. Seems like we're stuck. There's nothing to cancel. That's the dangerous part. But actually, it's not as bad as we think. Okay, a substitution is a substitution. And you can do a lot with a substitution, and it's all about the substitution. Repeat what I just said. A substitution is a substitution. And And it's all about we can substitute, what we can substitute. So here's how I see it. U equals x plus 3. U equals x plus 3 means x equals u plus 3. I mean u equals x minus 3. I might have accidentally said that incorrectly earlier. U equals x minus 3, our chosen substitution. Now we can rearrange that as well as x equals u plus 3. It's all a substitution is a substitution, and it's all matter. It's all about what we can substitute, and we go ahead and start spending your time, be creative, turn your expression all over. You have enough algebraic experience now. You have enough algebra background now. What good about that? What good do I bring for myself here? X equals u plus 3. X equals u plus 3. So instead of canceling things as usual, see, that's why I said it's a slightly different style. If you love math, this is a fascinating world of substitution right there. Okay. 5 times u plus 3, square root of u, du. And now the problem is turned simple. How is it simple? By the way, that factor, I can keep it from front. The square root u here can be multiplied to each of the term here. So the first term now, after pulling out that the constant coefficient in front, now I'm looking at u times square root of u plus 3 times square root of u. It's just a simple distributive law. Okay, and so now on my next board, I can just simply rewrite my current integral problem completely in terms of u. The first term is now a u to the 3/2 power. So confirm with your algebra, review your algebra to see how the u square root of u turns into that. Okay, because we have seen this all over back in the day we were doing derivatives, and also back in the days we were doing antiderivative. So there's no need for me to break it down too far here in details anymore. Okay, and then plus the 3 square root of u, the 3 square root of u term. Right here, the 3 square root of u term is exactly the same as just 3, and in your experience, u to the 1/2 power. And now we are so ready for the real action. Okay, so first integral, so it's 5 times, the first term now gives me 5 times u to the, so 3/2 plus 1. Okay, so it's 5/2 divided by 5/2. Okay, and think something will cancel later. Plus, now I have 3 times u over u to the 3/2 power, but divided by 3/2. And now I can plus c. And so I'm going to clean out the terms a little bit by simplifying these coefficients to its simplified form before I put back the original u variable. So this is 5 times 2/5, okay, u to the 5/2 plus 3 times the 2/3 times u to the 3/2 power plus c. And so now that's what I meant by simplifying out the coefficient. And so now the next step here is to bring back the original meaning of our u substitution. So u was x minus 3. U was x minus 3. Right here in at our substitution point for that. And so in that way, I am going to just bring it back to whatever it was. So 2 times, okay, x minus 3 in parentheses 5/2 power, okay, plus another 2 times, okay, x minus 3 to the 3/2 power, okay, plus c. And this is our final answer for that. We've had a problem done. Okay. All right, and so what if? So I chose for the solution I've just finished now, I chose u to equal x minus 3. But before I get started into that way, I had indeed, if you remember from the beginning of this problem right here, I pointed out the 2 different choices. And as I said, up to this point, I'm very firm with what I have been teaching everyone. A substitution is a substitution. There is no right or wrong substitution as long as we know how to make it work. Okay, so here's the, what if we went with the other way? What if we chose u to equal square root of x minus 3? Look at how creative we can be sometimes. Okay, and at this point it's extremely important that you've got to master your calculus 1, your differential calculus understanding. Okay, so if we substitute for that, u equals that, then partially this will become 5x times u with a dx. But there are still a lot of unfinished work here, in a sense that this x here did not get washed away. The dx here also did not get substituted away. Okay, let's continue. So you can see kind of in similar experience you have done back in part in the same problem, but back in earlier solution, the different solution. Here, how I'm doing this, how I'm seeing this. If u equals x minus 3, I mean square root of x minus 3, then I can square both sides, turning that into a u squared to equal x minus 3. Algebra again. It's just all the algebra. So I always have my right to keep reminding my students, you gotta get your algebra going, so that the more you get your algebra strengthened, right? The more creative you can be, and the better it can be for your calculus courses and those much higher courses later on. Okay, so it's all because I made a u to equal square root of x minus 3. So creatively I can go u squared to equal x minus 3. Okay, so that means even further that u squared plus 3 will equals x. U squared plus 3 equals x. Does that look familiar? So that means I can partially move on to another step right here. That x now can be substituted by u squared plus 3. So now it's 5 times u squared plus 3 times u dx. See how easy that start looking? U squared plus 3 doesn't look so hard at all. In products with u can eventually be distributed into each term here. Okay, but we still got hung up with that dx right there. So now in the way how I'm seeing my expression, my current relationship, then x now is a function of u. X now is a function of u in the way how it looks. So we can go dx du, treating u as a variable, then dx du. That's why I said you gotta really, at this point, in order to see through with this problem right there, review your differential calculus understanding. But you see, when you have a function like that, you can write it as a dx du. So dx du is the same, equals to, as far as the derivative in terms of u, 2u. And the derivative in terms of u is 2u, so that means we can consequently, allow me to tear out with a little space here, we can consequently turn our substitution as dx is to equal, I'm going to multiply that du differential to the other side, 2u times du. What good did that bring for me? What good did that bring for me? dx equals 2u times du, completely in terms of u. So that means in my next step, well, I just want to bring that coefficient in front. So how about 5 in front, u squared plus 3 times u. But now the dx here is substituted by the 2u du. 2u du. That now gives me a total, so 2 can be again brought in front, so it's going to be 10, and then there's a u times another u right here, so it's really u squared plus 3 in product with u squared du. We are successful again because this is so ready for action, and then we can just go ahead and distribute out that u squared for each term here, turning our integral into a u to the 4th plus 3u squared. And now I believe I can leave it here for viewers and students of mine to pick up from the rest of that. The answer might look slightly different from the answer you expected that we've had earlier, okay? But in the end, that is the work, how we're doing it, okay? In the end, that's what it is, okay? All right, and so on my other board, in case you haven't given it a try yet, then 10 u to the 4th plus 3u squared du. Okay, now we can write that first term. It's just now a very simple integral of two separate terms. So first term gives me 10 times u to the fifth over 5 there, plus, and now 10 times 3 here is a 30 times u cubed over 3 right there. Okay, plus c. And so now that gives me, so this 10 here cancel with 5, that gives me 2 u to the fifth, plus, now that's 30 divided by, cancel with 3 right there, that gives me 10 u cubed plus c. All right, but now don't forget, u itself equals square root of x minus 3. Okay, so now I'm looking at 2 square root of x minus 3 to the fifth power plus 10 times square root of x minus 3 to the cube power plus c. Okay, and that is our final answer. And as I said, the answer here might look slightly different with the answer that came out from the previous solution, but it should be the exact same answer.